Hi, this is Olivier Stodig, and today we're going to cover another installment of the parametric box model. This is version 005, and we're going to cover the dynamic aeroelastic analysis using our CCX model and SciPy. So we can actually do some very fancy stuff just using CCX and what's included with Python libraries such as SciPy. So today we're going to look at doing a modal analysis. So that's a dynamic aeroelastic analysis. And all we need to do to do that is to solve an eigenvalue problem. And we can even speed this up using sparse matrices in SciPy. So to do this, we're going to start first looking at some of the approaches that are typically used to solve these sort of problems. And then how we can implement those approaches in our code. So the first thing we need to do is extract the mass and stiffness matrices from our CCX model. And then we can already do a normal modes analysis. Then the next thing that we have to do is calculate some aerodynamic matrices. So that's aerodynamic damping and stiffness matrices, and add them to the problem. And then once we have all of these matrices, we can actually solve the aeroelastic stability problem to check whether we have flutter or divergence occurring. And we can do that over a range of velocities. So in this video, we're going to cover the code and then actually run it to see what the outputs are. So stay tuned. So this might look quite complicated, but actually you will recognize some of the terms in this. So the notation here is M for the mass matrix, D for the structural damping matrix, and K for our structural stiffness matrix. And Q, Q dot, and Q double dot are the generalized coordinates and the derivatives of that with respect to time. And we can set this equation to 0 because we don't actually have any external forces applied for this aeroelastic stability analysis. So we're just solving the problem subject to the structure and the aerodynamics. And the aerodynamics are introduced through these two other terms. So we have our aerodynamic damping matrix and our aerodynamic stiffness matrix, which are factored with this rho, which is the air density, and v, which is the free stream velocity that flows of air that flows over our wing. So the thing we can do with this equation is that we can rewrite it in terms of a combined vector of our generalized coordinates and the first derivative of these coordinates to build the system matrix Q, which gives us effectively this equation here on the right. And if we then define our generalized coordinates as a function of time, like so we're actually assuming a oscillatory response, then we can solve this aeroelastic equation as a generalized eigenvalue problem, or as a classical eigenvalue problem, actually, where we have as a solution our a vector of complex eigenvalues and the matrix of eigenvectors. Moreover, we can find that the vibration frequencies and damping ratios of our system are contained in these eigenvalues, which appear in complex conjugate pairs once we've solved our eigenvalue problem. And from these vibration frequencies and damping ratios, which we can find at different velocities, and if we want to, at different rho values for the air densities, then we can determine if the system is stable or not by looking at the value of this damping ratio. So if the damping ratio is 0 or negative, then we have an unstable system, which also corresponds to eigenvalues which have positive real parts. Flutter in particular corresponds to any unstable solution that has an oscillatory part, so anything that has a non-zero imaginary eigenvalue part. And divergence corresponds to the non-oscillatory solutions. Okay, so now we know how we want to solve this system. Then the question is, how is this best implemented using Python? So it turns out that there's some really interesting capability in SciPy to solve these sort of eigenvalue problems. And if you look on the SciPy webpage, you will find this in the user guide. This is a section on sparse eigenvalue problems with RPAC. And there's a lot of additional information you can read through here. But as you see, the main problem that this solves is very similar to what we just had in our previous slide. And the interesting thing about RPAC is that you can actually solve very large problems and find only a certain number of specific eigenvalues in the range that you're interested in. So the traditional approach here with RPAC, the description you will see says that eigenvalues with large magnitudes are easier to find. And if you set this to the opposite, which is this option to find small eigenvalues, then you could run into problems. And that's why they recommend you use the shift invert method, which is explained here in these equations. And that allows us to solve our problem quite efficiently, because for flutter and divergence, typically we're only interested in a certain number of lowest frequency modes. So we're looking anything that any modes that are closest to 0 and above. And of course, it depends on how complex your problem is. But in our example, in a minute, we will only look at the first 10 modes or so. So this shows you how you can actually implement this eigenvalue solution problem with RPAC. And it comes back to a very simple equation. One line here in which you specify your system matrix. In this case, it was X, how many eigenvalues you want, and then some options with respect to RPAC. And actually, because we have a complex problem, complex eigenvalue problem, we will be using the eigs solver rather than the eigs-h. Okay, so this is the latest version of the code. Then the README, you'll find the reference to this post here, which includes the code release 005. So if you want to try this out, please download the code that's linked here under this tag. Okay, so if you look at the code contents, the parametric box module has changed a little bit. So there's some updates here to the header. And we can see that we need to call input 4 for a composite Calculix modal Aeroelastic analysis. And otherwise, the code is very similar to what we had previously. If we look at our input 4, you'll see that it still uses our composite wing. So it has the composite plies in here, the orientation, the composite layup. We're now calling an input file that's called ccx normal modes mat out. The reason for that is that we don't actually want to run a full ccx analysis. We just want to recover the stiffness and mass matrices from ccx. And that is, we'll have a look at that in a minute. That is what that file does. Otherwise, the input is very similar. The other change down here is that we have another process flag called run modal Aeroelastic, and that's now set to true. We've switched off the run post, and because we're not actually going to post-process the ccx output in the traditional way, because there's no deflection output here. And then we also have some additional parameters that are required for the Aeroelastic analysis. So we tell the model which Aeroelastic, so which aero inputs to use, and those, if we look at it, are imported from the eigenvalue analysis module, which we'll look at in a moment, which is the one that actually does the modal Aeroelastic analysis. And we also set the number of modes that we want our model to include. So this is the number of aeroelastic modes that we want to solve for. And in this case, we've just set it to a small number, 10 modes, so that we can do this analysis fairly quickly. Okay, and in terms of where this is implemented, if you look at our main function, you'll see that there won't have been any changes prior to running our CGX model, and there have been no changes prior to running our executing our FEA, which is executing Calculix. The changes come in afterwards. So instead of doing a post-processing or precise coupling analysis, we now have this run modal Aeroelastic option. So if that's true, then we call the modal Aeroelastic function, which has been imported from our eigenvalue analysis module. And by calling that, we basically enable us to recover the normal mode frequencies, and then all of these which are related to our flutter and divergence analysis. So we have our velocity vector, the frequencies as a function of velocity, the damping as a function of velocity, and then some dictionaries here which give us an indication of when flutter and divergence actually occur. Okay, and that's it basically. So once we have that, we should be able to do whatever we want with that output, whether that's processing it somewhere else or plotting it. There are already some plotting functions in the modal Aeroelastic module, which I'll go through in a minute. So if we look at our Aeroelastic eigenvalue analysis module, this is new in this version of the parametric box code, and it basically has a few inputs here at the top, which this one here is an aerodynamic input for a plate model, which is not the one that we're calling from our parametric box, but it is used in some of the test cases, which I'll show in a minute. And then we've got our box aerodynamic input, which is very similar to what we've had with a precise input. So we have some information about the planform, and in this case, because we set it to none, it's similar to the precise explanations that I gave previously in the previous video, where actually we're reading the planform from the box model. So these edge points on the wing planform are defined from the box model. Then we define how many strips. So this is the strips for the strip theory. So we're still using a modified strip theory in this case, but it's dynamic one this time around. The root alpha is set here, but it's not actually used by our flutter analysis because there's no static loads on our wing. And then we have some information here about the air density and the velocity range that we want to analyze. So we're setting our starting velocity in meters per second, and end velocity in meters per second, and starting increment. And then there's a minimum increment here that the code doesn't cut back further on. So this can be useful to play with if you have convergence problems of the code or of the mode tracking specifically. But anyway, the defaults here should be fairly robust. There's some information here about the mode tracking threshold. Again, this is probably a fairly reasonable value. This will be changed by the code if necessary up to a certain point. Beyond that, if it doesn't find matching modes, it will reduce the velocity increment to try and improve the matching between two different velocity increments. If you're not too familiar with flutter analysis and mode tracking, then there's probably quite a few good references, which I'll try to reference in the blog post that can help you understand what this is about. And CL alpha is our lift curve coefficient. So again, we're using a sort of analytical value of 2 pi, which in this case, we actually, we have this variation. We have a variation of assumed lift across the span of the wing. So we've modified our error slightly, and I'll show that in a minute. Okay, so if you execute this module, you'll see that by default, you're running some test cases. So it will run through the simple plate test first, and then through a parametric box test. Both of those can be run independently of the parametric box module. So they rely on inputs that are already available in the test data, test eigenvalue analysis folder. So you'll see that there's 3 different folders here. And they already have some data in there. And if you want to run those test cases, you'll just have to make sure that you read the instructions at the top of these functions, because you will need to run the CGX, execute CGX to generate the mesh file, and then execute CCX to generate the normal modes output, so the matrix output that we need for this module. So we're not actually generating a new wing here in this module. We're assuming that CGX and CCX analysis has already been performed. So that's the simple plate test, which runs through both some normal modes checks on the simple plate, which is a composite plate, and then it does some simple flutter analysis checks on plates with 2 different layups. And then the same with the parametric box test. So that's actually the same inputs as the input number 4 from our parametric box. So if you look at this one here again, the laminate that's described here actually corresponds to our parametric box test in this module. So it does check that you're getting the right flutter and divergence outputs at the end of the analysis. And both of those execute, if I just go into the simple plate here, both of those execute the main function of this module. And the main function has a few inputs. The main inputs being a master file for the CCX analysis. So that's what we actually saw in our previous module. It's the CCX normal modes mat out file. So if I have a quick look at what that looks like. So here I'm looking at the composite plate example, but it's exactly the same input that you'll see in the box example. So we have a top level input file here, which includes our CCX mesh, and it also includes our composite shell definition and some boundary conditions. And we're actually doing so this is the actual frequency analysis. So we're requesting 15 normal modes from this analysis. But the analysis that we're actually pointing to in our here is the CCX normal modes mat out. So to compare that, it's this one. Okay, so here we just requested frequency 15. In this case, we have exactly the same input, except that we actually have this frequency solver matrix storage and then the 15. And what that does is tell Calculix that actually we don't want to do the modal analysis. We just want to store the mass and stiffness matrices calculated by Calculix. And these matrices are then stored to what's called the .mass file and the .sti file for the stiffness and mass matrices respectively. And then we've also got this .dov file, which the syntax of this is explained in the Calculix manual. But the .dov file actually has a list of degrees of freedom. So the first, each line has a node number, then a dot, and then a direction associated with that node. And you'll see that there's exactly the number of rows in this file as there are degrees of freedom. So number of rows that exist in the matrices. The other thing to note here is that we actually have some repeated degrees of freedom. So this looks a bit strange because you wouldn't expect there to be any duplicates. The reason for this is that we obviously defining a shell model, and that internally Calculix expands this to a 3D element model. However, in this file, it still outputs the shell reference nodes and the degrees of freedom and the directions associated with that. So what we'll do when we do our Aeroelastic analysis, when this file gets read, to define the eigenvectors for the Aeroelastic analysis, we actually take an average of the deflections of repeated or duplicate degrees of freedom. So this basically gives you a lookup of the nodes with respect to the CCX model, and then the how those nodes match up with the rows of the stiffness and mass matrices. And if we look at the mass and stiffness output files have exactly the same format. Obviously, one includes mass details and the other one stiffness terms. But each one has the three columns. So the first two columns are indicating the row and column of the respective matrix, and then the third value is a float, which corresponds to the matrix value at that position. So there's everything here that we need to build our mass and stiffness matrix within our new eigenvalue analysis code. We've just gone through the normal modes analysis. So this is actually, we have two different ways of calling our main function. One is to simply call it to calculate the normal modes, in which case you only require these inputs. The other one is to actually call it for aeroelastic analysis. And in this case, we also add the aerodynamic input, which references one of those inputs that we had at the top of the file. And if we now look at what the main function actually does, so that's the one right here at the top, then we can see that we initially have some reading of files. So we're actually reading some of the boundary conditions here. And then we're also looking at the loading the degree of freedom file and some the lookup table that corresponds to that. And we also read the shell mesh node locations. So this is important because it gives us some information about the splining nodes that we're going to have to use to go from our structures model to our aerodynamic model. So all of these are inputs that we need for the aeroelastic analysis. Not all of them are required for the modal analysis, just the structural model, but yeah, you can see where those are called. Then the next thing is that we actually define, we actually read in our mass and stiffness matrix from these CSV files that I was just showing you. And we add them to this problem dictionary. So this problem dictionary includes all of our problem matrices, and we will build it up over time. So once we have these matrices defined, then we can actually do a normal modes analysis, and this is replicating exactly what Calculix would do internally. to solve the frequency analysis problem. So it's very easy once we have those outputs here, which is we're calculating the frequency in hertz, and we're also outputting some eigenvectors here. There's also, I think this function also outputs the eigenvalues, which you could request here. So if we don't have an aerodynamic input, all of the following is skipped, and then it just returns the frequencies at the end, which can be compared with what we get in Calculix. And just so you know that what it looks like, we have here an example of the normal modes analysis. Okay, so we can just quickly execute that normal modes analysis to see what the CCX output looks like. We see that it actually runs extremely fast, so fraction of a second here. And the output is contained in the .dat file. And you can see right at the top of the file, we've got this eigenvalue output, where we have 15 modes that are output, listing in each row the eigenvalue, and then the frequency real part. So all of these are, of course, real frequencies because we don't have any aerodynamic terms in here yet. And we have the frequency both in radians per second and then in hertz. So this is what we can compare to our omega output from our main function. Okay, so we've done our normal modes analysis using CCX. Now let's have a look at what's in here. So if we look at our get normal modes function, this implements the eigsh function that we saw in the SciPy manual earlier. So this is actually now calling the real eigenvalue problem using a sparse matrix approach. And it's, as you can see, it's very simple. It's a one-liner. Of course, we import our eigsh from the sparse SciPy sparse library. So we have both the eigsh and the eigs that we will use in a minute here. So we simply provide it with our stiffness matrix as an input and our mass matrix as a second input. In this case, we can actually do this rather than inverting the mass matrix and pre-multiplying our stiffness matrix here. So this is actually, eigsh has this capability to solve a generalized eigenvalue problem. So this is quite handy. And as I was mentioning before, because we're interested in the lowest eigenvalues, we set this sigma option here to 0 and request the output with LAM, which is a bit counterintuitive, I think, but actually, so this is telling the code that you want to request the largest eigenvalues, largest shifted eigenvalues, which then results in an output of the smallest ones from the script, actually. And then once we've got those eigenvalues and eigenvectors, we can simply calculate the vibration frequency from this in hertz through this equation and return that. For the aeroelastic analysis, it's important that we also pass out these eigenvectors here because that's what we're going to use as the degrees of freedom for our aeroelastic problem. So we will actually need to define aerodynamic eigenvectors from these structural eigenvectors, which will allow us to calculate aerodynamic forces. Okay, so if we go back to our main function, so if we define the aero inputs to the main function, we then have here a check that makes sure that we have requested an even number of modes. This is important because the code at the moment assumes that we always have a certain number of matched pairs of eigenvalues that get calculated. So the other thing here is that we are then actually calculating the modal mass and stiffness matrices. So that's simply pre-multiplying and post-multiplying our mass matrices and stiffness matrices by these eigenvectors. And that's important because we're actually going to solve our aeroelastic problem using factors of the normal modes analysis eigenvectors as the degrees of freedom. So whereas here our eigenvectors had as many degrees of freedoms as degrees of freedoms existing in the Calculix model, when we solve our elastic analysis, there will be a number of degrees of freedom corresponding to the number of modes that we chose here. Then the next thing is that we instantiate our error model. And this is actually using the same error model function that we used in the precise module previously. And this is just to allow us to reuse some of the functions that we had there. So we're calculating from the error model and the box model, we're calculating our plant form and then outputting our leading edge and trailing edge nodes. And that's a function of the number of strips that we defined on the wing as well. So once we have that, we can actually then calculate our aerodynamic eigenvectors. So this is important. So this part of the main function makes sure that we have eigenvectors for the aero analysis that are matching our structural eigenvectors that we calculated previously. And it also filters it down in terms of the degrees of freedom to make sure that, for example, if we have a box wing, we only interpolate either on the top or on the bottom surface of the wing, so we don't get any strange behaviors. So we have these nodes X, Y, Z here, which define the surfaces that we want to interpolate on. So if I scroll back up, we can see that here we simply said we want to interpolate any of the nodes using any of the nodes that are have Z positions. So that's the node XYZ column 3 that are larger or equal to 0. So for our box model, that means that we're interpolating using top surface nodes only. And we're also only calculating the eigenvectors using deflections in the vertical direction, because that's the main deflections that we're interested in for this example. You've got a plot flag here, which allows you to, if we toggle that, we can actually see an overlay of the structures and aerodynamic eigenvectors, and that can be quite useful. And other than that, it's quite self-explanatory. You feel free to have a look at this function in more detail. So there will be some things that I was mentioning previously about filtering out the nodes on XYZ that we're interested in, and then taking care of removing any duplicates, for example. And then also here we are actually setting any remaining boundary condition nodes to 0. So normally you wouldn't expect there to be any boundary condition nodes in the matrix, but because we're expanding to those 3D elements, the mid-side element nodes tend to appear in the matrix, and we want to make sure that those degrees of freedom are actually set to 0. And once we've got all of those reduced eigenvectors set up, we can use a simple 2D interpolation to calculate our arrow eigenvectors. Okay, so coming back to the main function, we now have our eigenvectors, which means that we can now calculate our aero damping and aero stiffness. These equations are explained in the blog. They are using a simple modified strip theory, which is now dynamic. So and we have one modification here. We're calculating the terms using a constant m theta dot or m psi dot term. So this is an average, and it's an approximation that allows us to do some fairly representative flutter analysis here. And once we have those new aerodynamic matrices, we can then combine that into our aeroelastic equation together with the structural terms and solve for our aeroelastic flutter and divergence velocities. Again, if I have a look at that function, you'll see that we start off by initializing these matrices. So anything that's preceded by a v underscore will be something that's output at every velocity increment. The flutter and divergence outputs here are actually they're lists of dictionaries where every dictionary entry is a flutter or divergence point. And then we start iterating over the velocities. So we have this whilst velocity flag is true, we increment, and this is actually happening at the bottom here. We actually append the current velocity to the velocity vector and then increment the velocity by the increment and set the increment the index for the matrices as well. There's some cases where this loop will exit. It will exit if the tracking fails, or if there's an error in the aeroelastic stability analysis. It will also stop whenever the maximum velocity is reached or exceeded. So if we go back to the top of this, we can see that we start off here with another loop. So this loop makes sure that we can track the aeroelastic modes between velocity increments. And as long as that's not true, we don't move on to the next increment. So the first thing that we do here is to solve our, to actually build our system matrix Q, which we had in the slides at the beginning of this video. And then we solve the complex eigenvalue problem using the eigs function now. So we simply input our Q matrix, request the number of aeroelastic modes that we previously set in our input, which was 10 here for our box model. And then we still have the sigma shift offset and which LM option, which tells us that we want to output the 10 lowest eigenvalues and mode shapes. And then there's some mode tracking checks here that happen. So to do this, we use a MAC PX criterion, which comes from a reference here from a conference paper. There are many different tracking algorithms. This may not be the best one, but it allows us to calculate something that looks very similar to a modal assurance criterion matrix. So it allows us to make sure that between two increments, we can identify which modes are closest to each other, and then resort the modes to make sure that we have that we know what those mode evolutions are over the velocity range. So if we go back to our modal analysis, okay, so we have our MAC-XP output here, and then we have a function that processes that and outputs a flag here that tells us whether it was able to track the modes or not. If it was able to track the modes, then we have this mode order here that we can continue to associate our outputs from the eigenvalue to our different matrices. So we have a matrix here that tracks the mode order from one velocity increment to another. Then we have the matrix of the eigenvalues that are output at each velocity iteration. And at each iteration, we're adding a new line to this. This is why we're padding it with a 0 value here, and we'll associate we will actually populate that new line in a second. And we do that also with the frequency matrix in hertz, the damping, and the flutter and divergence matrices, which are not output directly from this code, but they're used for debugging if needed. Okay, so if the code was able to track the modes, then we continue through here. And for each unique mode that was identified by our mode tracking algorithm, we extract the eigenvalues and also extract in memory the mode shape, so that at the next increment of velocity, we can compare our new mode shape with the previous one. And then we calculate these either the frequency and damping for oscillatory modes, or simply the damping if we know that we don't have an oscillatory mode. So this is the case where we have 0 imaginary value for the eigenvalue. And we also do some checks here to see if the damping is negative, then we can identify flutter or divergence occurring. So once we've finished our velocity increment, we finished our loop over all the increments, we can then output our flutter and divergence outputs, and we can also plot these over the time history. So this is a simple plotting function which allows us to plot the frequencies versus the velocity, damping versus the velocity, and the real and imaginary eigenvalues with respect to the velocity. Okay, and we're also exporting this data so we can inspect it later on if needed. Okay, so let's try and run this. So we've already set our main function input to input 4, which is our elastic input. So we should be able to just execute this. I've put a breakpoint here at the end of our Aeroelastic analysis in the eigenvalue analysis module, just so that we can actually look at the full output in a minute. So, whoops. Let's have a look at our parametric model. And now I'm just going to execute this. So bringing up the debug console and run. So this takes about a minute to run. So the first few lines of output probably look quite familiar. So we have a duplicate of our input. We've already generated the CGX input file, and now we're running the CCX analysis. So this is our output folder, and we can see we've generated here the mass, stiffness, and degree of freedom output files. And now we're actually running this aeroelastic stability analysis. It takes a bit of time to just read those files in again and generate the matrices, but once it's started in the velocity increments, it should go fairly fast. Okay, so we've just generated here the aeroelastic output, and we've also got as a first output our normal mode frequencies, which we can compare with our CCX output if we were to run the normal frequency analysis. And then we can see that we've actually incremented our velocity by 5 meters per second up to 136 meters per second. We've got a warning message here saying that the tracking failed at just under 140 meters per second because one of our modes actually probably moved outside the tracking range. And to solve that, we could just request more modes. But in that range, we've already found some divergence and some flutter happening. So if we actually look at what's been generated in our output directory, we now also have some plots, so we can actually visualize these flutter and divergence outputs. So we can look at our, let's say, our frequency plot with velocity. So we have our modes here of increasing frequencies. And if we match this up with the frequencies from the normal modes analysis, we can see that, yeah, we've got one mode which is roughly starts around 6 hertz or so, 6-7 hertz. We've got a second one which is just under 40 hertz, third one around 45 hertz, and then so on. although we requested 10 modes, we can see that because we have the complex conjugate eigenvalue output, we're actually only plotting the first 5 complex modes here. And as we can also already identify that there's something strange happening here. So we've got a mode that goes from oscillatory to fully damped. We can also look at our damping plot. We've got our first mode here, which corresponds to this blue line, and this is exactly what we've just seen here. We get fully damped behavior around 91 meters per second, which is just before we have the divergence happening, and it picks up the divergence as this mode goes through zero damping, at which point it goes to a frequency of 0. And then the flutter is also picked up here. So we have a mode 2 flutter at a velocity of 116 meters per second, which corresponds to this orange line going through 0. And we've got mode 3 flutter, which is a bit harder to see here, going through 0 at 136 meters per second. And the other thing that we can do is also, of course, look at our eigenvalues. So we've got the imaginary and real parts here. And again, this is part of the processing that we do to calculate our frequency and damping. This is the original data. So we can see that we're tracking these eigenvalues quite well through our frequency, through our velocity range. The other thing we can do, of course, is look at our actual matrix output. So if I just close these down, we've got the breakpoint here at the end of our Aeroelastic analysis iteration. So we can actually have a look at what's output here. So if we just have a look at the V as simply the vector of velocities, so we can actually see what the calculated velocity increments were, and then V omega and V damping are simply our frequency and damping matrices, which each line corresponds to one of the velocities from our velocity vector. So we start off with frequencies here that are very close to the normal mode frequencies, and as we go along, we see these changing. So we have our first mode that goes to 0, and so on. And we can also have a look at our, let's see, the damping is going to be similar in terms of format. So originally we have positive value of damping here for all of our modes, and as we go along, we see that first we have this the first mode here, which goes from 100% damped to completely undamped. That's our divergence happening here, and then we can see that later on we also have our flutter happening here in the second mode and the third mode right in the last increment. Now, sometimes it's worth noting that the modes are not necessarily output in an increasing frequency order. So it might be worth checking this V mode ID matrix, which tells us the correspondence between the mode numbers and the order and the other matrices. So here we actually have duplicates for each of the eigenvalues. So this tells us what the numbers are in the eigenvalue matrix, which is this V eig. And we can see that actually we have got to start off with it's what we would expect. So we have the lowest mode frequency, which is our mode 1, and then mode 2, mode 3, mode 4, and 5. So these are nicely ordered. And as I said, sometimes you'll see that the eigs algorithm with RPAC actually doesn't necessarily output this in the frequency order. So it's worth checking that these modes are actually what you expect them to be. Where we can see that there's no major changes. We do have some switchovers here, which are correctly tracked by the algorithm. And we can also see here that in the last increment where this is failing, we have our mode 1 frequency. Well, not the frequency, but our mode 1 is starting to those identified mode 1 eigenvalues are actually moving apart further and further. And I think in the next increment, these are moving out of this one is moving out of the range, which is why we get that error. But this is basically our Aeroelastic analysis. So we have everything that we need to then decide when flutter and divergence occurs and to do further processing if required. And if we let that run to the end, we can see that this completes without any errors. And we can have the outputs here forwarded on to another function if we wanted to, if we set the outputs equal to main at the bottom here. Okay, so this was demonstrating Aeroelastic modal dynamic analysis using Calculix and Python. Thanks for listening.